Our next presenter is Daniel Colvett. He's currently working to complete his PhD in systems engineering from the University of Alabama, Huntsville. He has been serving as an engineer with the Department of Defense for 10 years. During his tenure with the DoD, he has served as a systems engineer in domains such as software assurance, cybersecurity, and logistics. He's worked for AMC, MDA, and DevCom AVMC. He's written or co-written 5 published papers related to his dissertation research. Today, Dan will be presenting his work, Quantitatively Analyzing Defensive Actions in Cyberattacks. Dan, I'll turn it over to you.
UAH. The work that I'm going to present today is an attempt to quantify defense actions and evaluate different defensive strategies during cyber attacks. So part of the modeling technique that I'll be going over in the next couple of slides is called Petrinets, with players, strategies, and costs. I just want to point out that before I begin that my project is part of a larger research program at UAH where we have 5 interconnected research projects that are all using the same modeling technique. The diagram over to the right, if we're starting from the top, reading left to right, the first project is taking cyber attack entries and creating Petrinet models for those cyber attacks. The second project, which is my project, is adding defender and user representations to the models as the cyber attacks are attacker-centric. The third project is taking the individual's attacks and making an attack campaign. So we're looking at combining attacks such as SQL injection and Crosssite scripting, where an attacker may run multiple attacks to compromise the system. The fourth is verifying and validating the models that we've created. And the fifth is using machine learning to analyze different defense and attacker strategies within the models. Just an overview of Petrinets. Petrinets was originally proposed in Carl Petrie's 1962 dissertation. Petrinets have been extended many times to include colored Petrinets, time Petrinets, and stochastic Petrinets. The basic Petrinet is a 6-tuple model that contains a place. A place represents a state or condition in the system or process being modeled by Petrinet. A place can be represented by a circle in the diagram to the right. P1 and P2 are places. If a place contains a token, the state or condition is interpreted as true. So in the example to the right, P1 has a token, so we would say that P1 is true and P2 is false. The marking at the start of the execution is considered the initial marking. A transition represents an action or event that may change the state or condition of the system being modeled. A transition can be represented by a rectangle or a line. It can be filled or it can be unfilled. So in the diagram to the right, T1 is a transition. A transition has input arcs and output arcs. Arcs are represented by lines connecting places of transitions. So the arc between P1 and T1 is an input arc, and the arc between T1 and P2 is an output arc. If all of the transition input places contain a token, we say that the transition is enabled. An enabled transition may fire, which is interpreted as a change in the system. When a transition fires, all of the tokens in the input places are consumed, defined by the arc weights, and output tokens are placed in the output places. So starting with the left diagram, at step 1, T1 is not enabled because P1 is an input place that is not marked. At stage 2, P1 is marked, T1 is now enabled, and at step 3, T1 is fired, it has consumed the token from P1 and has placed the token in P2. On the right diagram, in step 1, T6 is not enabled because all the input places are not marked. In step 2, T6 is enabled because P4 and P5 are marked. When T6 fires, it consumes a token from P4 and P5 and places a token in P7. A little bit more of the same, just more input places here. Is in step 1, T1 is not enabled because P2 is not marked. In step 2, T1 is enabled because P1 and P2 are marked. In step 3, T1 fires. It consumes a token from both P1 and P2. Now T2 is enabled. T2 fires. It consumes the token from P3, and it places a token in P4 and in P5. One of the first extensions of Petrinets that we'll talk about is something called an inhibitor arc. So an inhibitor arc prevents a transition from firing, even if all of the input places have tokens. So following the steps through, in step 1, T1 is enabled. It consumes the token from P1 and places a token in P2. Now T2 is enabled. It consumes the token from P2 and places the token in P3. P3 is now inhibiting T1. In step 4, even though P1 is marked, T1 cannot fire because P3 is inhibiting T1. Note that an inhibitor arc is different, or can be shown differently by a small circle shown at T1. This is just modeling basic systems. So like on the first diagram on the left, we have a drawer assembly process. The drawer can attach a handle unless both the drawer and the handle is available. If that's available, then the transition will fire and the process will be complete because the drawer will be assembled. The next example shows a conveyor belt transporting items. When the transport transition fires, the transport is complete and token goes in conveyor finished place. The conveyor is reset and then ready for the next item to transport. So Sakruska and Farragut created earlier work called Petrinets with Players and Strategies. We call that PNPS. Our work extended the PNPS formalism by adding costs, so we call our extension PMPSC. We added representation for relative cost of actions taken, and we resolved some ambiguous definitions that was in the original formalism. Here's an overview of a PMPSCnet. We'll go over the different components over the next few slides. But in this net, we have an attacker trying to brute force log into a computer. The defender can detect the attack, then decide whether they want to block the attack, which is transition T4, or if they want to monitor the attack, which is transition T5. So if they're running a honeypot situation and they want to see what the attacker is capable of, instead of blocking the attack, they may choose to just monitor the attacker. If the attacker logs in, which is T1, he has one action he can take. He can try to gain root or administrative access, which is transition T3. In original Petrinets, if two transitions were enabled at the same time, one of the transition would arbitrarily be chosen to fire first. So in this diagram, we have a case where T1 and T2 is enabled at the same time. In a PMPSCnet, we use fire rates in a stochastic process to choose the transition that's going to fire. The fire rates are relative, so that means that the higher the rate, the more likely a transition is to fire. So in the example below, T2 is more likely to fire than T1 because its fire rate is more than double of T1. Next part of our extension is the idea of players. PMPSCnet can have one or two more players. So in a cyber example below, we have an attacker and a defender. The players have competing or cooperative objectives. Places can be player observable, and transitions can be player controlled. A player controlled transition means that the player can change the fire rate of the transition. So in the example below, red transitions are attacker controlled and red places are attacker observable. Blue places are defender observable, and blue transitions are defender controlled. All other transitions is what we call non-player owned. A PMPSC strategy is a player's desired fire rates based on the marking of the player observable places. So in the example below, we can see that defender can see P3 is marked. If the goal is to block the attack, the defender would choose to raise T4 fires rate and decrease T5's fire rate. There are two types of costs in a PMPSCnet. The first cost we're going to describe is the fire cost. So in the example below, we have a case where T1 is fired and then T3 is fired. If T1 and T3 have a cost of 2 and 1 respectively, the total cost of these actions would be 3. Now the total costs don't necessarily have to be a summation, but I'm just using a summation for this example. The second cost is associated with the player changing the fire rates, the transitions that they controlled. So again, this does not have to be a summation, but for this example, we're going to use the summation. Let's say that a player has 3 transitions that they can control. If all 3 transitions have a fire rate of 0 and the player changes the fire rates to 404, the total cost would be 8. If those same 3 transitions had a fire rate of 123 and the player changed them to 224, the total cost would be 2. So what I just previously described was the informal way of the PMPSC formalism. This is our more rigorous way to write out the formalism. Since we've already went over them in the previous slide, I'm not going to go over all these. I'll just point out a few examples. So number 7 is gamma. which describes the strategies. It's defined as a mapping from possible markings of a player observable places to the desired fire rates for each player's control transitions. Number 8 is the cost, which is the firing costs. The first, C fire, and then the second is C change, where if the player changes the fire rates, they incur a cost. If you want to read more about the formalism, we have a couple of publications in the references. And part of this research I'm going to describe is when adding the computer system user representation, I needed a way to measure the impact to the model. Part of that is I'm going to use machine learning. In particular, I'm going to use reinforcement learning. Reinforcement learning is a machine learning training method based on rewarding desired behaviors. The diagram from Sutton and Bardo below provides a good overview for reinforcement learning. We have a couple of elements here. We have an agent who is doing the learning, the environment, which is everything outside of the agent, an action, which is what an agent can change to impact the environment, the state, which is a representation of the current environment, and finally the reward, which is the consequences of the action taken. We can map the reinforcement learning concept to a PMPSCnet as follows. The agent is the player, the environment is the PMPSCnet, the action is changing the fire rates of player control transitions, the state is player observable markings of the PMPSCnet, and finally the reward is the final state achieved, positive if it's successful, negative if it's not successful. In particular, we're using an E-greedy reinforcement learning technique. In a greedy learning technique, the agent will always take the action that previously led to the greatest reward. By always choosing the best outcome, the player may choose not to explore other options, so they can get stuck on a local minimum. To overcome that, we use an E value. The E value is the probability that an agent will go explore other actions instead of taking the most previously rewarded action. So for example, if we have an E value of 0.04, we'd say that 90% of the time, 96% of the time, the player will take the greedy action, and 4% of the time, they'll explore other options. Exploring is important because it avoids the agent becoming stuck on a local maximum and go search for a global optimal answer. So enhancements to some of the previous work, and part of my research is the previous work was limited to only evaluating 2 different rates per transition and limited to 2 players. This was because of a state space explosion issue in the simulator that we had wrote. For example, if you have 2 fire rates, there's 134 million combinations that needed to be tested. But if you increase that to 3 fire rates, the number increases to 78 billion. The previous simulator, whenever we increased it to 3 fire rates, it would run for about 20,000 runs and then the system would just crash. We mitigated this by using a relational database. There's a trade-off, though, that the previous nets now take about 4 times longer to run. However, the simulator has ran for up to 9 days and without any crashes. Another enhancement is adding representation for the computer system user, which we'll go over in the next couple of slides. So this is a Petrinet for the computer system user. In particular, this is a computer system user using a web application. So we can think of this as logging into the bank. So the first state there under user session, this would be a computer user just logging into the bank website. The second phase is the HTTP GET phase. This would be the computer system user retrieving like account balances and other information about their bank account from the web server. The third phase is the computer system user may decide to pay a bill or post information to the website. So in a banking example, this could be paying an online bill where the user inputs data such as amount owed and day and date to send the money. And the last is the decision phase where the user decides whether to close the application or perform another action. At any of these stages, the defender can choose to block the action, or they can choose to flag the user request or allow the request. If they flag or block the user action, this is considered a false positive, and the defender would be penalized and given a negative reward in the reinforcement learning framework. This is just another example, but with a desktop application. Here, the user is either opening something like a Word file or opening Microsoft Word itself. The user does some work and decides to save the file. At any point, the defender could block the application from launching, block opening the file, or block saving the file, or again, they could flag the user from doing these activities, which would be a false positive. So KPEC entries in the previous models are attacker-centric. They do not have details for the defender. Another part of my work is enhancing the KPEC models with defender representation for common defense and depth tools. So for example, the diagram on the right, in previous models, we would just have AT12, which would be the defender detects spidering is occurring, but there's no detail on how the defender detects it or what the different actions are. On the left side, you'll see I've added transitions MT9, MT10, MT11, MT12, and these expand on the defender's actions using defense in depth techniques, such as web application firewalls or network intrusion detection. And this allows us to more realistically look at defender strategies and actions. So I'm going to go over cross-site scripting. We use cross-site scripting as a attack model because it consistently ranks high on the OWASP top 10. An example of cross-site scripting is an attacker putting a malicious script on a user form or maybe like a news website that allows for comments. Now, the script could be something benign as just making a pop-up that says hello, or it could be something malicious, such as making the user mine Bitcoin for the attacker's wallet. We use the MITRE's Common Attack Pattern Enumeration Classification Database, which is the baseline description for the attack. The resulting net that we came up with was validated by a panel of subject matter experts in cybersecurity, which you can see is reference 7. I'm going to go over the net, but if you want full details on all the transitions and places, you can look at our previous work that's referenced. So I'm showing the whole cross-site scripting net just for reference. There's 4 phases: explore, experiment, exploit, and goals. Over the next few slides, I'm going to go over these individually. I just wanted to point out that all of these are connected in a larger net. It's not really clear in PowerPoint when you see them chopped up, but this is what the full net looks like. So the first phase is the explore phase. In this phase, the attacker is probing the site to find all URLs and possible data entry forms. So for example, at AT2, the attacker will automatically spider the website using an automated tool such as the harvester. There's other methods such as proxy tools to find all the links and manual brute forcing. The left side, when AP2 is marked, this is an example of the strategies. So for example, when AP2 is marked, the defender would choose to set the rate of AT12 to 10, AT13 to 0, and AT14 to 0. This would lead to an average reward of negative 19.75. For the attacker, they would set the rate to AT2 to 0, AT5 to 10, and AT8 to 10, which yields an average reward of 7.9. This is the results of the reinforcement learning algorithm, and for this particular state, this is the optimal answer that the reinforcement learning algorithm discovered. The next phase is an experiment phase. In the experiment phase, the attacker is trying different techniques to see if web application is vulnerable to cross-site scripting. So for example, at BT8, the attacker may try making a bogus forum post with a specially crafted cross-site scripting string in a forum. Again, you can see the strategies on the left. So I'll just go over the defender. For example, if AP14 and BP1 are marked, then the defender would set the rates to BT15 of 0, BT16 of 10, BT17 and 18 set to 10. This leads to an average reward of negative 24.52. In the exploit phase, the attacker is actively carrying out exploits against the web application. So example, CT2, the attacker may post a crafted cross-site string to the forum. When a normal user goes to that forum, the user's browser will load the forum, but will also see the string as an executable script and it will execute. Again, this could just be as simple as a pop-up, or it could be sending sensitive information about the user's computer back to the attacker. Again, for the strategy, for the defender, if AP14 and BP18 and CP1 is marked, then the defender would set the rates to CT18 of 0, CT19 to 0, CT20 of 0, CT21 to 0, and CT22 to 10. And this would give them an average reward of negative 12.7. In the goals phase, the attacker is trying to carry out their end goal. This may be to read the application's data to gain login privilege to a machine, whether that's the user's machine or the web application server itself, execute unauthorized code, or modify the application in some way. For the defender, an optimal strategy, if AP14, BP18, CP23, and DP1 are marked, is to simply set the DT11 rate to 10. This yields an average reward of 10 for the defender. So here are the results from the reinforcement learning algorithm. The left diagram shows the average reward over time as each episode executes. As we'd expect with reinforcement learning, we can see that the reward increases as time goes on. We ran this for 500,000 episodes, but I just cropped it at 100,000. The right chart blows up the actual 100,000 runs to the first 10,000 runs, because the first 10,000 runs is where most of the learning occurs. That's where we see most of the variation. So the average reward at the end of 500,000 runs for the defender was 3.06 if no computer system user was present. The average reward if the computer system user was present was negative 20.42. So we can see that the computer system user impacts the defender reward as we would expect. Another comparison for when the computer system user is present is, as expected, if the computer system user is present in the net, the defender will choose a different strategy 80% of the time given the same state. So for example, if the marking for the exploit phase is BP 17 equals 1, the defender strategy without the computer system user would be to set CT21 and CT22 to 10 and all the rest of the transitions to 0. However, if the computer system user is present, the defender decides to set all of the transitions to 0 and set none of them to 10. Just to recap the reinforcement learning results, the defender reward increased over time. Most of the variation, again, occurs within the first 10,000 episodes. Representation for the computer system user lowers the average reward and changes the defense strategies. This is especially true if we see the same state more than 30 times, then it's almost certain that the defender will change their strategy. So PMPSCnets can be used with reinforcement learning techniques. We were able to run the reinforcement learning techniques without data sets, and the inclusion of the computer system user impacts the defender strategies. With this technique, you can answer questions such as, does implementing defense solutions increase the chance of tet-to-tat, or does it significantly impact the computer system user? You can also start looking at analysis such as, what's my false positive rate for certain defense strategies, or what's the cost of implementing certain strategies. With that, here's my references, and I'll turn it over to the forum for questions.
Yep. Can you hear me well?
Yes. Yeah.
Let's see if my camera will actually work. I believe it is.
It's working. Can you read the question?
Yes, sir, I can. It's
Okay.
one from Dr. Wilson. Would we be able to use these techniques to help solicit cybersecurity and cyber resiliency requirements? Yes, we should be able to. We're currently trying to implement this at work on a UAV system. In particular, we're looking at CIMA, which is cyber and electronic attack environment. And for resiliency, we're looking at how long, not only can the defense block the attack, we're looking at, can the defense recover from the attack before the mission is over? So for example, if you have a UAV that has a flight time of 15 minutes, but it takes your defense solution 17 minutes to recover, that's no good, because the UAV would be out of the air at that point. The defense solutions, as far as soliciting the requirements, since we don't know what the defense solutions are ahead of time, we just kind of have generic blocks that says defense solution here, and we can model what the numbers would have to be to meet the mission requirements. Does that answer the question?
Waiting to see, so she can't respond with her voice. So we're not sure. Thank you, Daniel. So I think, Beth, you can, yep, it answered the question. So Beth can follow up with you directly if she has any other questions. Thank you, Daniel.
Thank you. I appreciate the opportunity to present my work.
Mm-hmm.
Thanks.